Hello, my name is Hanna Suzuki from Bedford High School in Massachusetts. Today, I will be presenting my research on machine learning-based heat risk estimation for outdoor sports. As we all know, it has been extremely hot in recent years. 2023 had the hottest summer in the past 2,000 years. 2024 was the hottest year in history. It was 1.8 degrees higher in Fahrenheit than the 1991 to 2020 average. And though 2025 is expected to be milder thanks to a La Nina, it is still likely to be the third hottest year behind 2024 and 2023. So, due to these hot temperatures, heat-related illnesses, or HRIs, are a critical threat for anyone outdoors. This includes heat cramps, heat exhaustion, and heat stroke. HRIs occur when your body can't regulate its temperature and overheats too much. In 2023, over 2,000 HRI deaths were reported in the US. A research study says over 10,000 deaths are attributed to HRIs annually. HRIs are especially critical for outdoor athletes in the summer months. They are among the top 3 causes of athlete deaths, and this includes 77 deaths in the US since 2000. Among them, 84%, or 65 of them, are teenagers. This is because younger generations are more vulnerable due to higher metabolism. To assess the risk of HRIs, wet bulb globe temperature, or WBGT, is known to be effective. It is a numerical index that indicates the heat stress on the human body in direct sunlight. It takes into account solar radiation, air temperature, humidity, and wind speed. WBGT is unique in that it uses measurements in direct sunlight, unlike heat index, which measures the air temperature and humidity in the shade. This is unrealistic and not very helpful for athletes who are on fields and courts that have no shade nearby. Because of its effectiveness, WBGT is recommended by athletic associations at all levels. Here you can see a very common heat safety policy for high school athletes in the US. This is recommended by the National Federation of State High School Association, which most public high schools in the US belong to. As you can see here, this policy has 3 regional categories. Category 1 is the most northern region, and Category 3 is the most southern region, and then Category 2 is in between them. For each category, there are multiple heat alert levels from the safety green level to the riskiest black level. Each heat alert level has certain WBGT thresholds for activity adjustment. For example, if the WBGT is higher than 86 degrees Fahrenheit in a Category 1 state, then you should not do any outdoor activity. It's just too hot and dangerous. If it's between 84 and 86 degrees, though, your outdoor practice is limited to an hour with 20-minute breaks distributed through the hour for safety. In this heat policy, different regions have different WBGT thresholds. So Category 3 has the highest thresholds and Category 1 has the lowest because athletes in the southern regions are more acclimated to heat. This heat policy, it's great, but it's not used often in high school sports because WBGT meters are expensive. So to address this issue, math models are created to estimate WBGT from meteorological parameters. However, some of those parameters, such as solar radiation, are not commonly available for non-experts like athletes and coaches. So, the objective of this project is to propose a method to estimate heat alert levels from meteorological parameters that are commonly available even for non-experts. This method uses supervised machine learning that learns the relationship between those meteorological parameters and heat alert levels and classifies a given set of parameters to a particular alert level. There are several research works to estimate heat risk with machine learning methods. They all rely on some specialized data, though, which are not readily available for non-experts, such as time series WBGT data, solar radiation data, and physiological data like heart rate. So this project is different from those existing work in that it relies on common meteorological parameters only. This project uses those decision tree and random forest algorithms to build supervised classifiers. They take a set of meteorological parameters as input, the air temperature, humidity, cloud cover, precipitation, wind speed, and the time. And then the classification output is a heat alert level. As you can see in this table, the heat alert levels are from level 0 to 3, indicating the safest to the riskiest. These decision tree and random forest classifiers are built and trained with over 15,000 meteorological data samples from the summer of 2024, which were collected from 290 cities in the US with an online database of NOAA. This raw data set is imbalanced though. As you can see here, the number of samples significantly vary across the heat alert levels. So the raw data set is randomly undersampled so that each heat alert level has the same number of samples. Then a subset of the undersampled data set is used as the test data, which has 652 samples. The raw data set is also oversampled with the smoke method to produce the training data, and the training data and test data are then combined to create the cross-validation data, which has 46,429 samples. Here are the classification accuracy of the decision tree and random forest classifiers. The training accuracy, testing accuracy, and cross-validation accuracy are the accuracy against training, testing, and cross-validation data, respectively. As you can see, the decision tree classifier's accuracies results vary. So this implies that the classifier overfits to that training data. Therefore, 3 major hyperparameters are adjusted to avoid this overfitting. I analyzed how training and cross-validation accuracies change by varying each hyperparameter. For example, this figure here shows how the two accuracies change with different values of max depth, which controls the maximum depth of a decision tree, and its x-axis represents the max depth values from 1 to 20, and its y-axis represents classification accuracy. 1.0 equals or means 100% accuracy. So as you can see, the training and cross-validation accuracies are almost equal when this hyperparameter is low. But when it exceeds 10, the training accuracy becomes apparently higher than the cross-validation accuracy, which means overfitting occurs. So I set 10 as the upper limit for max depth. I then did the same thing to set the value ranges for other hyperparameters. Then I ran a grid search to find a hyperparameter condition, a combination where training and cross-validation accuracies meet. As a result, the training and cross-validation accuracies met at 91%. So this is the decision tree classifier's accuracy after overfitting is avoided. The accuracy results of the random forest classifiers are close enough with each other, and so it's reasonable to conclude that no overfitting occurs. The random forest classifier's accuracy is 99%. I was also then curious about the contribution of each meteorological parameter. So I analyzed the contribution of each input parameter to classification performance. I measured the permutation importance for the individual parameters. The importance of air temperature, humidity, time of day, cloud cover, wind speed, and precipitation are 0.67, 0.53, 0.35, 0.11, 0.11, and 0.102 in the decision tree classifier. Then in the random forest classifier, they are 0.63, 0.48, 0.34, 0.08, 0.05, and 0.03. This indicates the air temperature, humidity, and time of day contribute the most. The proposed classifiers are efficient and lightweight as well as accurate. Their training times are 0.29 and 7.46 seconds, respectively, and their classification times are less than 0.01 and 0.02 seconds per sample. Their storage consumptions are 60 kilobytes and 8.7 megabytes, and they are lightweight enough to be used in web apps. Here is an example of a web app that can be used with smartphones. As a conclusion, this project demonstrates that machine learning-based heat risk estimation works effectively and efficiently with the meteorological parameters that are readily available for non-experts like athletes and coaches. As for future steps, I plan to collect extra data samples from NOAA this summer and train the classifiers further with them. I also plan to develop a wearable device that runs the classifiers. Since I'm a tennis player, I will use the device during tennis practice and matches to verify if it can issue early warning with vibration or sound for precautions and activity adjustments. This concludes my presentation. Thank you for listening.